a second introduction to entropy. So, with qualitative applications. Now, if you go to chapter 6 in the book and you start reading it, it immediately goes to these examples and it talks about whether it violates the laws, and it does a lot of hand-waving discussions on whether there's a violation of the second law or whether it isn't, or first law, and it has a lot of hand-waving discussions. And and I've tried to always teach it kind of in that fashion, the idea of, but there's no way when you can't just do these hand-waving discussions. So what I'll do is I'll just recap these laws, and then I'm going to go right into, you have to jump ahead into chapter 7, and then go back to chapter 6, because there's no way, you need to have some equations. You can't just do hand-waving discussions on whether there's a violation in the laws. I tried to do it so many times, every time it's an epic failure. So, chapter 6 in the book does a lot of qualitative, right, not quantitative examples. And in principle, it makes it more complicated. So let's just recap the first law, right? So this is a second introduction, but okay, so we have all this right here. Work on. So thermal contact with the system. We have energy balance. It can be written in this form, adiabatic system, work on the system. We have this other stuff. Now what's important here is the second law, and then I'm going to do this to emphasize the fact that this is an what? Isolated system. So if I have a stick man in the box, does it know what is outside the box? No. If I have two stickmen in the box, they can't talk to each other and determine what's outside the box. If it's isolated, it doesn't matter. So this is for an isolated system. Okay, so remember that what we've learned so far, what you've memorized so far, is the second law of thermodynamics, an equation expression related to an isolated system. Of course, there's equation of state things. And then for an isolated system, this change in entropy from state 1 to state 2 has to be greater than or equal to 0. If the process is reversible inside, that means that there was no change in entropy from state 1 to state 2. So if two stickmen are in an isolated box, arm wrestling, before and after the arm wrestling match, there was no change in entropy if it was a reversible arm wrestling match. Okay. So, reversible process. Okay. This is the key part. A process must satisfy the first and second laws of thermodynamics. So there was a question, is a system 100% efficient if Q loss was equal to 0 given the first law? No, because that didn't mean that it was the whole system. You need the first and second laws, really the third and the 0th too, but really it's these two that matter, and others are just special, circumstantial or little things to help, but these are the main two laws of thermodynamics. And all processes, from you sitting in the classroom to whatever it might be, airplane travel to whatever it might be, every process you can think of satisfies the laws of thermodynamics. So if you're going to engineer something, you need to make sure that what you engineer is going to be based off of satisfying the laws of thermodynamics. Here is a famous quote. The second law of thermodynamics is without a doubt one of the most perfect laws in physics. So those who are saying that they don't need thermal the rest of the career, you might want to reconsider that very idea when you can see a quote that says that it's the most, thermal deals with one of the most perfect laws of all of physics. Any reproducible violation of it, however how small. So a grain of sand in the ocean to a supernova, no matter how small or large, any violation of the second law will bring the discovery of great riches, and a Nobel Prize. So if you find any violation in the second law, the reason is because of that single violation, you will solve, because of that one caveat, no matter how small, you will solve all the energy problems. You'll find a violation in the second law of thermodynamics. You will solve all the world's energy problems. Okay, so there's a lot of other things, but that was the main thing. So if you find a violation, I'm going to go through an example of proposed perpetual motion machines and how a violation of the second law will basically give you a device that produces work and cools the system. So you have a turbine system that produces work and cools the turbine to absolute zero. It's a perpetual motion machine, and you just give it a little kick, and it starts running, and there's work output, and the work output is in the process of cooling that system to absolute zero. And so there's always work output because absolute zero is an asymptotic, right, approach, so you're always getting work out of your system. Well, that has nothing to do. So I'll give you an example of a violation of the second law where those are the ramifications. Okay. Now, just one little side note. So a student asked, me, he was asking after class, are there limits to the rate of heat transfer? So is there a fundamental limit on how quickly heat can be transferred, like the speed of light? And so he was asking this, and I'll do evaporation condensation stuff, so I know there was some kinetic theory limits to evaporation and condensation, but then I was thinking about conduction, so let's just consider this. I have block A at temperature A, and I have block B at temperature B. Now these are perfect homogeneous pieces of copper with no defects, and they are in a box isolated from the surroundings. And what happens is they spontaneously form a contact with each other. So this is all vacuum, and so they spontaneously touch each other, and because they're at different temperatures, a temperature gradient is, so if I were to plot, so I'd have some temperature A and temperature B. And so I would immediately get some temperature distribution as they contact each other. And it turns out that within this context, and you can use Fourier's law of heat conduction, within this context, that this heat temperature distribution is established faster than the speed of light. So there's a violation in relativity. So there's such a thing as relativistic heat conduction, where you have to take into account what? Just make a guess. Relativistic heat conduction has to take into account, make a guess what? What's that? Relativity? Okay, relativity plus something else. Respective properties plus something else. Quantum mechanics, yes, plus something else. Yes, where molecules are, things like that, but not necessarily molecules, but related to that. Another guess. Look at the screen in bold. The second law of thermodynamics. Okay? So this theory has to take into account the second law of thermodynamics. And basically, okay, it's a debated theory, but what happens is it puts an entropy generation rate as a governor on the rate at which that temperature distribution can, so it can't be generated faster than the speed of light, that temperature distribution. And the governor is the second law. But the ramifications of all of this is you can use this theory and relativity to prove the second law of thermodynamics. Okay? Or you can take it the other way around. You can take this theory and the second law and prove relativity. So basically it puts relativity and the second law of thermodynamics on equal playing ground. And you can divide one from the other. So I'm just saying this to reinforce the idea that maybe not now in your current job or your next job, but the second law of thermodynamics is going to have equal playing ground in the future as relativity. It's one of the most perfect laws. It's just beautiful stuff, but anyways, it's still a debated theory. But I'm just pointing out, second law is important.
Now, can you repeat that? Because didn't you say that it violated the second law because of the fact that it happens to...
No, Fourier's law of heat conduction, where you just based off heat diffusion, that law is a simplified version. And when I go through this scenario of two blocks, it says that law doesn't say that there's a limit to how quickly the temperature distribution can be set up. And so it turns out that it happens instantaneously faster than the speed of light. So that law is not correct, it's an approximation.
Fourier's isn't.
Fourier's.
But it does not violate. It does not violate.
I guess it doesn't violate, it just violates, well, it violates either relativity or the second law, because they're on equal playing ground. And so you have to take into account the second law, and then from that you can prove relativity, or you can take into account relativity and can prove the second law, derive the second law. So the second law and relativity are on equal playing ground. You can derive one from the other using this theory. Yes?
Does the difference in temperature between the two affect the rate at which...
Yes. And so if you think if this is absolute 0 and that's 1,000, there's going to be, well, there's different distributions, right? So there's going to be different rates of entropy generated. There's going to be a larger heat flux. And remember the tedious question form of the second law? T ds equals Q. So the change in entropy is dictated by heat transfer and the temperature of the system. So if I have a larger distribution, I'm going to have a larger heat flux, so that's going to influence. So if I have A and B, I'm going to have some Q. There's going to be a heat flux. As I change the temperature, make TA greater than TB, then I'm going to have a larger heat flux. There's going to be some average temperature here. And so I'm going to have, as this heat flux changes, I'm going to have a different corresponding change in entropy associated with heat flow. Okay. So that was a little digression, but I think it's worth noting the correlation between relativity and the second law of thermodynamics. So how do we check if there's a violation of the first law? Energy balance. So what have we been doing throughout the course? We've been drawing a schematic, we've been writing out energy balance, we've been simplifying it. So basically we've been checking if there's a violation in the laws of thermodynamics, right? So energy in minus energy out equals the change in internal energy in my system. And of course, each one of these, heat, mass, and work. Okay, so I have three forms. I can break up each one of these into three forms. And so there has to be a balance. So if I have no energy coming in and I have work going out, that has to be at expense of the decrease in the internal energy in my system. Otherwise, there's not going to be a balance. So a perpetual motion machine requires that. It's not going to sit there and work forever, because if it's producing energy, it's going to be at the expense of the decrease in internal energy of the system. At some point, that internal energy has to approach zero for it to keep on operating. And there is such thing as absolute zero. So how do we check if the second law is violated? Entropy, okay, entropy is playing a role. So if you look here, there's energy balance. So we could say entropy balance. So entropy balance. So I had this expression here. And now I want to do entropy balance. So it's the same type of idea. So let me draw a system. And I'll put 2 stickmen in it. A boy and a girl. I don't know. But so I have 2 stickmen in my box. And then, of course, I can have energy in and energy out. And of course, this energy in, energy out can be in the form of heat, mass, and work. And I can have a change in internal energy in my system. And based on energy in and energy out, I can also get a change in entropy in my system. So with entropy balance, here I have this expression. Now in entropy balance, I have entropy in. I don't like that pen. I have entropy in minus entropy out. And I have some plus some other term here. Equals the change in entropy of my system. This is the entropy generated. And now I have my entropy in minus my entropy out plus my entropy generated equals the change in entropy of my system. So just like this was the internal energy in my system at state 2 minus the internal energy in my system at state 1. This one here represents the entropy of my system at state 2 minus the entropy of my system at state 1. So if my system goes through a cycle, what is the change in entropy of my system if it goes through a cycle? Someone said 0. Anybody disagree with that? No. Why? Because if you go through a cycle, state 1 is state 2, so it has to be 0. Likewise, if I have a system that goes through a cycle, what is the change in entropy of the system after it goes through one cycle? 0, or energy, because state 2 is state 1 after a cycle. You go through a cycle. So if you go through a cycle, that means you have to have a balance between energy in and energy out. Now with entropy, this might be 0. You have to have a balance here. So there can be some entropy generated if there's an imbalance between this. Okay, so I have that. I have 2 systems in, and I have entropy in minus entropy out plus entropy generated equals that. And so here, with my entropy in and my entropy out, before I had heat, mass, and work for energy in. Now in this case, entropy is not associated with work. The entropy transfer is not associated with work. So in this case, I only have heat and mass. Heat and mass. And if you remember the tedious question form of the second law, what is entropy? Well, that's a tedious question. TDS question. So I can look at, so from this, I can say that entropy in is going to equal Qn over T. And I'll put a B there. So I had this tedious question, and you see that.
What's the B stand for?
Boundary temperature. So I'm going to have some heat in, and right here there's going to be a boundary temperature where the heat is coming in. Yes?
So if it was ES, does that make S in like the rate at which?
Yeah, so this is kind of an approximation, so the way I've written it. Really there's an integral and it's dq and but I'm just saying I'm just doing the simplified way of writing this out. And I'm just saying heat, tedious question. I can write entropy in is Qn over Tb. This takes into account that there's an entropy in at absolute 0, which is 0, so you're looking at a difference, but it's relative to some reference point. But then that same the entropy out also has the same reference point, so when you look at the deltas, I can just do the reference between the in and out. But so I'm just pointing out that I can do this. Now with mass, just like we had an energy per unit mass and an enthalpy per unit mass, we have an entropy per unit mass. And if you remember, we just multiplied m times small u and m times small h in our energy balance equations. Now we're going to say m times small s. And so this is mass in, entropy in. And so I can do the same thing. So let's write out this whole thing in this form, simplified form. So I have Q in over temperature, boundary temperature, plus some mass in and entropy per unit mass in, minus Q out over a boundary temperature, plus mass out and entropy per unit mass out, plus Sgen equals the change in entropy in my system. Now, if you recall, what have I focused on when I talk about a property? So how do I define this? S in equals S at what? At the temperature and pressure of the input. So if I have some mass coming in here, there is a control volume, and it has a temperature and pressure. And if it might be coming in at a given rate, and we've already done like mass flow rates, volume flow rates, velocities, size of the pipes, we've been all doing all this stuff. Everything else still applies. We have a velocity, there's a temperature and pressure. So there are thermodynamic properties of what's coming in. And so here I have a mass coming in, and we associate with that mass is be a temperature and pressure, so I know the entropy per unit mass of what is coming in. Likewise, if I know the temperature and pressure and the type of mass leaving, then I know the entropy per unit mass. Well, I don't really know, but somebody did a lot of work for me and tabulated all this stuff for me for most materials. Unless you're an engineer for DuPont or 3M making a new material, then you will have to go through that process of defining what the entropy per unit mass is, because if that fluid is used in a heat exchanger, they need to know if they're violating the second law of thermodynamics, so they need to know the entropy per unit mass. Okay, so we have that S at Tn, Pn. Okay, so the same applies with everything else. So I have this. So let's just circle this expression. And let's say this is a full energy balance. Still a little bit simplified, but you could write this out for every problem. After you write your cartoon, write out your full first law, simplify your first law, you can write this out and then start simplifying entropy balance. So let's start crossing out things based on the fact that this, I am going to say that my two stickmen in the box are in, that it is an isolated system. So what can I do to this energy balance or entropy balance expression? Yes?
You can cross out the heat and the mass and then out.
Dun, 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 dun.
So all you have is
No, I don't have entropy in. There's no heat in, there's no heat out, there's no mass in, there's no mass out. All I have is this expression right here. So the change in entropy in my isolated system has to equal the entropy generated. Now, let's think of what you memorized for the second law of thermodynamics. It was for an isolated system. And I already had this here. So I can write below that, what, on this side right here? Someone tell me? Integral. Okay. And where what has to hold? Where this has to be, right, greater or equal to 0. So that means that the entropy generated, this is an isolated system from energy balance. This is what you memorized. They're the same thing. It's just saying that the entropy generated follows this reversible. So if I have two stick men who are arm wrestling, and it's all reversible heat, they do all this arm wrestling, it all ends up being reversible heat transfer during the arm wrestling match, then it's reversible arm wrestling, and there's no entropy generated. So if I have an isolated system, anything that takes place within this box, either I'm going to have no entropy generated, or whatever takes place within, as soon as the boy and girl stickmen look at each other, there's entropy generated. I don't know how you, I mean, whatever, however you want to look at it. Or there was nothing that happened. Right? I guess, I mean, there's a lot of ways we can go into that. But anyways, entropy generated has to be greater than equal to 0 for an isolated system. So now let's say I have a system that is not isolated. So there's allowed to be heat and mass transfer. Do you think the entropy generated can be less than 0? No. So basically what it's saying is the isolated system defines the entropy generated, and it has to be greater than equal to 0. And if I put this in rate form, I can do the same thing in rate form, and I can do everything in rate form. All that means is there's a rate of the arm wrestling taking place, or whatever, if they have cycle arm wrestling, or however you want to look at it inside. But also the rate of entropy generated has to be greater than equal to 0. Yep, entropy generated always has to be greater than equal to 0. And if I have a system or a cycle that's reversible, then the entropy generated is going to be 0. That doesn't mean that I don't have a change in entropy in my system. Yes?
Is the entropy generated always going to be delta Q reversible with the even for a non-isolated
No.
system?
No. So this is a convenient form, because this just deals with irreversible heat. I mean, in principle, we could write this in terms of mass transfer between the two stickmen between, and there could be irreversible mass transfer or something like that, and heat. I could make this more complicated for reversible. If I have an isolated system, there could be mass transfer between entity A and entity B, and heat transfer, but it all has to be reversible heat and mass transfer
Well, what I'm
for the entropy generated or for it to be reversible.
What I'm asking is if we had, I mean, obviously if we had a non-isolated system, then the change in entropy isn't going to be that. Would that still be the equation for the entropy generated portion?
No, you want to, so from here on out, you want to write that. We will solve for, on a regular basis, the entropy generated for a variety of different processes. That's what we will solve for. And then based on finding that, what is the entropy generated for that energy producing or energy consuming device, we will use that entropy generated expression to define the second law of efficiency, which will tell us how efficient this process can be. So this one is convenient for the first introduction to the second law of thermodynamics. And not to write too long of a complicated expression related to the second law, because we just do an isolated system. Talks about entropy greater than equal to 0, reversible delta S equals 0. But in engineering practices, this is this full expression here, the full entropy balance. Now granted, these could be integrals and more complicated. This is the way to do it.
So the entropy generated will be an equation that's derived from the
We will derive the entropy generated based upon changes in the system, energy in, energy out, entropy in, entropy out, heat in, heat out.